Let me now prove this theorem 1. So recall that we have seen that the map f p to the power n, which takes x to the power p to the power n, is a homomorphism. Then it follows easily that the set of x such that f p to the power n of x is equal to x is a subfield. And it contains, of course, fp. But these are exactly roots of x to the power p to the power n minus x. Let me call this polynomial in what follows qn of x. Of course, this subfield is exactly the splitting field of qn. Is a splitting field of qn. And since qn does not have multiple roots, this can be seen, for instance, by verifying that qn is relatively prime with its derivative. Indeed, this derivative is just equal to 1. So there are exactly p to the power n of the roots. So we have this subfield of p to the power n elements, and this is a splitting field of qn. Of qn is exactly the field of roots of qn, and this is a field of p to the power n elements. So conversely, we want to show that any field of p to the power n elements is a splitting field of qn. Let the cardinality of k be p to the power n and alpha an element of k. Then alpha to the power p to the power n minus 1 is equal to 1, provided that alpha is non-zero. Indeed, the multiplicative group of k has cardinality p to the power n minus 1. So any element of k star to the power p to the power n minus 1 must be equal to the unit element. Alpha is a root of x to the power p to the power n minus x. And 0 is, of course, also a root. K consists of roots of qn. And this also answers the question why there is a unique subextension of fp bar, which has qn, p to the power n elements. This is just because this subextension consists exactly of the roots of qn. The unicity of the subextension of the embedding of, well, not exactly of the embedding, but of the image of the embedding of k into fp bar also follows. Let me now formulate and prove a few other properties of finite fields. These are very much in the spirit of Theorem 1. So let me probably call them Theorem 1, 2, 1, 3, and so on. So Theorem 1, 2 claims that fp to the power n contains fp to the power d if and only if d divides n. One direction is the multiplicativity of degrees and towers. Indeed, in this case, we have that the degree of f p to the power n over fp is equal to the degree of fp to the power n over fp to the power d times the degree of fp to the power d over fp. So this is n and this is d. So we have d divides n. Conversely, suppose that d divides n, then if x to the power p to the power d is equal to x, the same is true for x to the power p to the power n. Since taking x to the p to the power nth power is just iterating taking x to the power p to the power d. So f p to the power d is contained in f p to the power n. So these are very small theorems. Theorem 1, 3. It's better maybe to consider all of them as parts of the Theorem 1. So Theorem 1, 3 says that f p to the power n is a stem field and a splitting field of any irreducible polynomial p from fp of x of degree n. So the part about stem field is clear. So indeed, a stem field of p has degree n over fp. So this is f to the power p to the power n. Then the part about the splitting field can be shown, for instance, as follows. Let alpha be a root of p. So alpha is an element of f to the power p to the power n. Then qn of alpha is 0, since qn has as roots exactly all elements of f p to the power n. So p divides qn, and so p splits in f p to the power n. this has a simple corollary. So Qn is the product over OD dividing n of all p, where p is irreducible monic of degree d. So proof. Indeed, we have already seen that all such p divide Qn, since the stem field is f p to the power d, and this is contained in f p to the power n, so Qn of alpha is 0 if alpha is a root. So they are relatively prime, of course, and their product divides Qn. Also, Qn has no multiple roots, so there are no multiple factors either. And then what remains to prove is that there are no other irreducible factors of Qn. So let R be an irreducible factor of Qn. Then if alpha is a root of R, Qn of alpha is 0, of course. So this means that Fp of alpha is contained in Fp to the power n, and this means this means that Fp of alpha is Fp to the power d, where d divides n, and so this means that the degree of R divides n. So there are no other irreducible factors.